Okay, welcome to lab number 3 for Engineering 2151. Today we're looking at capacitive and inductive circuits. In the lab, we're just going to use capacitive circuits to demonstrate the points. But what we see here in our circuit, we've got a few different things now, right? We first off have a signal generator that's going to give us an AC source now, right? Previously we were dealing with DC. Now we're dealing with AC, okay? And then we come to our capacitor, right? And our resistor. And what we're going to do is measure the voltage with an oscilloscope and show you what happens when we change the voltage and frequency on the signal generator. Now actually we're going to set the voltage to a certain voltage and leave it there. But then we're going to change the frequency, right? Because when we look at this circuit, again, it's just a simple series circuit with a capacitor in series with a resistor. But when the frequency changes, the resistance, actually we call it reactance now, the reactance of the capacitor changes, right? So what we have are the two equations, one for the inductance, one for the capacitance, but XC is equal to 1 over 2 pi FC, and XL equals 1 over 2 pi, or sorry, that's not 1 over, is equal to 2 pi FL. Okay? So now, when we start, say, with our frequency at a low frequency, right? So if this C or F is small, then XC is large. And as we increase the frequency, XC gets smaller and smaller, so less voltage is going to be dropped across it. Okay? So when we measure our voltage with our oscilloscope, right? This is our oscilloscope. And again, it's just a voltmeter, but it shows you the voltage, right? You can see the waveforms, right? With DC, it's just flat and boring. With this, we're going to have sinusoidal waveforms. Way more exciting, right? Okay? So again, when F is small, the voltage across here is really small. Okay? And then as the frequency goes up, less and less is being dropped here and more gets dropped across the resistor. So the voltage is going to go up. Okay? But something else happens too, right? So let's take a look at our sine wave, right? So here's our sine wave. This is our V gen. Okay? And what ends up happening is when these things are changing, it creates a phase shift. Okay? So what ends up so what it's going to look like is, say for example, when this is extremely small and this is very large, then everything becomes in phase. So the VR, right, so the voltage across the resistor is going to be very much like this. Okay? But in the other case where this is very large and this is very small, what ends up happening is it gives it like a 90-degree phase shift, right? So if this is our peak here, then this is the zero cross here, right? So our sine wave is going to look like this. And again, because it's VR is way small, right? Okay? And when you see that this peak, and actually this isn't a very good representation, when that peak is at the zero cross, you know that it's a 90-degree phase shift. Okay? So what we end up doing is we start drawing these impedance triangles. Okay, so let's say, for example, we have XC is very large. So VR is very small. Our triangle looks like this, because R is in the real axis. XC comes way down like this. So our phase shift here is almost 90 degrees. And then what we call the resultant here, this is actually called Z. So Z is the impedance. Okay, so we're throwing around some new terms, right? XC, that's the reactance, and the overall resistance of the circuit, the impedance of the circuit is Z. Okay, so that's why, like, if you buy your speakers and they're 8 ohm, well, 8 ohm, okay, that's resistance, but they always call it impedance, right? Well, because there's more, it's not just a pure resistive thing, a speaker, right? It has inductance in it. So it has an impedance, not just a straight resistance, okay? Okay, so there is the case where XC is very large. In the other case, right? XC is very small, R is very large, Z, right? So this angle here now is almost 0. Okay? But then you have all points in between where you have things that look more like this, right? So we have all points in between. And that we'll have to deal with. So when I'm looking at the scope, like my first measurement, I really don't have to measure the phase shift because I'm going to see that it's almost 90 degrees. And then my very last measurement, I'm going to see that it's right in phase and that it's a 0 phase shift. Okay? But then again, all points in between, right? So again, now we can just use straight Pythagorean's theorem to go through and calculate these different things, right? So Z equals the square root of R squared plus XC squared, right? And then theta is the arctan XC over R. Okay? And these equations are true for the voltages as well, right? So we can say V gen equals the square root of VC squared plus VR squared. And then I'll do this over here. Tan equals, or theta equals arctan VC over VR, right? And these should come out to the same values, hopefully, right? Okay. So then what we're going to do, right? So we got to go through a process of how to measure these things. Now our oscilloscopes now, we have these pretty complicated scopes now. And it'll actually do these readings for us. But when you go out and say, for example, you might have to measure this at some point and read what a phase shift is, and you don't have a really good scope, well, here's what we can do, right? So here, let me just, I'm going to take this stuff off. Right? So if this is our generator voltage, and say, for example, this is so this is V gen, this is VR. Okay, so the way that we measure this, or the way that I would measure this, is I measure the time in between the two peaks of the waveform. right? So I would bring these down on the axis because this is a graduated axis here, and you can make a measurement what this time is here. And I'm going to call this delta t. Okay? And I can say that delta t over the period is the same as the phase shift in degrees over 360. Okay? And so in order to calculate this, I can manipulate this equation a little bit, and I can say the phase shift in degrees equals 360 delta t times f, because if I flip t up here, it becomes f, right? So that's your period, and 1 over the period is the frequency. So there's our equation to calculate this. So what we have to do is just measure this delta t, and then we figure out what our phase shift is. Okay? So, that's the first part of the lab. Okay? So the second part of the lab, so the first part, what we got to do, we got to make up a table. So the table's going to look like this. We're going to have frequency here, right? We're going to have 100, 500, 1,000, 5,000, 10,000, 50,000, right? And across here, we're going to measure VR, VC, okay, VGen, and this is the measured. And then you'll have one VGen calculated. Right, so these two squared equals this. And then we're going to have theta. Okay, so we're going to go through these different frequencies and we're going to measure these different quantities. Okay, so get this set up previous to when you watch the second part of the video where we do the demonstration, and then we're going to go through and we're going to do all these different measurements. Okay? Okay, so the other thing we do with this lab, okay, this is part one. So for part two, okay, make sure you get this down. You can pause the video, make this chart, okay? So for part two, okay, we're going to do this. I'm going to draw that like this. This is a switch. I'm the switch. I'm just going to be moving wires back and forth, right? And, okay, this is, okay, and actually, sorry, I did that the wrong way. Okay, so let's start this again. This is part two for the third lab, okay? And we're going to measure the voltage across here. Okay, so we're going to look at how the rate that this charges up, okay? So one of the things that happens with the capacitor, right, is we can use it for timing circuits, okay? And it can be pretty useful for doing this. I mean, there's a lot of other ways we can create timing circuits, especially digitally now. We have counters and stuff that we can time these things properly and a lot more accurately, right? Even though this is a pretty good method of doing it, though. Okay? And so what we're going to do is we're going to start off initially with V equals 0. Okay? And the combination of these two components will charge at a certain rate. Okay, so with 68K, that's a pretty large value. So it's going to slowly allow current to flow through here and charge this capacitor up. Okay? If this resistance was smaller, it would charge at a faster rate. Okay? And then what we're going to do is, so to charge it right, we would have the switch in this position here. And it starts charging the capacitor. Okay? But then when we flip the switch down here, it starts discharging the capacitor because now it's connected to ground. And it'll discharge at the same rate, but in the opposite direction. Right? So what we're going to see, this is time, this is voltage. On the charge, it's going to charge like this, right? Where this is going to be our 12 volts, right? This is 12 volts, right? And it's going to slowly charge up to this, and of course it becomes asymptotical. It never actually ever gets there. But remember we said, you know, like there's tolerances, resistors, and stuff like that. We say it's close enough at a certain point, and I'll tell you what the certain point is in a second. Okay? And then when we discharge, the discharge looks like this. Again, it's just in the opposite direction. Okay? So the charge and discharge, so the instantaneous V is V, okay, in our case the 12 volts. Right? And it's either 1 minus e to the minus t over RC, or the V equals e to the minus t over RC. Okay? Depending on whether you're charging or discharging. Okay? So that's the equation. Okay? And then what we say, though, is after 5 time constants. Okay, what's the time constant? Time constant is tau. Okay, and that's as close as I can get to tau. Okay, and tau equals R times C. Okay, and that basically, when you put those two together, it comes up in a quantity of seconds. Okay, and we say that after 5 tau, the capacitor is fully charged. Okay? And when we do our measurements, essentially that's what we're doing, right? We're going to be charging this for a certain amount of time, and I'm going to go through the time, and it's going to be another chart that you're going to have to do, and then you're going to have to graph the results for the report, okay? So at 5 tau, it's fully charged. Okay? Okay, so what we're going to do, we're going to make a chart. It's going to be T and V, right? So it's going to be 0, 5, 10, 15, 20, 25, 30. Okay, so for the first, what's this? 7 measurements. We're measuring every 5 seconds. And we're doing that because it's changing rapidly. But then after 30 seconds, it starts leveling off. So we're going to go every 10 seconds after. So 40, 50, down to 180. So we're going to time this for like 180 seconds, 3 minutes. Okay? And then we're going to measure the voltage. Okay? And then what we're going to do is we're going to do the reverse and do the discharge. Okay? Starting at time 0. Again, it's the same timing. Again, the same things are happening, just in reverse. And then we'll measure the discharge. Okay, so this is charge. And then the discharge. So this is not DC and it's not DC. It's voltage charge and voltage discharge. Okay, so that's what we're going to be looking at for our lab number 3. Okay? So I'll meet you in the lab and we'll go through and make the measurements. Okay? Good. Okay, so this is a demonstration of lab number 3. So what I'm going to do is I'm not actually going to take results down right now. I'll provide you an Excel spreadsheet with the information on it for both part 1 and part 2. But what I do want to do is demonstrate how things are going to change. And I've got this kind of set up. I'm trying to record this kind of looking down on a scope that's lying on its back, and I'm hoping you can see this. So what we have here is the yellow waveform, the larger one, right? I can adjust this here, right? That's my input voltage, okay? And again, I'm just going to show you like conceptually what's happening, right? And right now I'm at the 100 hertz where it's a low frequency, so the capacitor is very dominant in the circuit, right? So very little is being dropped across the resistor. And this green line here is your VR. So like we were showing on the board with the impedance triangles, right? VR and R are very small. And it's also 90 degrees phase shifted. So if you look at the peak there, it's right at the zero cross. Okay? But now what I'm going to do is I'm going to change the frequency. And as I'm changing the frequency, you can see how VR now, the green, is getting larger because the capacitor is being less and less dominant, right? As the frequency goes up, XC is going down. So what we have now is more voltage being dropped across the resistor. And as I go up, and we got to keep changing things here. And again, the oscilloscope, and something that you should actually come in on work with as well, right? It's just an XY plot of your voltage. And time is on the X, and voltage is on the Y. And I can change the scale of the display. So as I go up, these things are getting larger and larger, and even though the green seems to be getting bigger, like it's only at 200 millivolts per division, and the yellow, the input, is actually at 1 volt per division, so the yellow is still much larger. So as we keep going up here, and now this will get progressively even faster and faster, right? But you can see now, like the phase shift is changing. Right now I'm at 7.4 kilohertz. And what I need to do is finally get up to 50 kilohertz. And by that time, these two waveforms should be right on top of each other. See, actually, so right now at 7.4 kilohertz, my peak-to-peak voltage on my input is 4.3, and my peak-to-peak on my VR is 1.79. And again, so these are just kind of going by what I've got on right now. So let's crank our way up here. So right now I'm at the 50 kilohertz. Let me adjust this down. Okay, so you can see it's still not 100% on top of each other. So the capacitor still is having some effect in the circuit. It's not totally dominated by the resistor yet. But again, I can keep going up. See, right now I'm at 200 kilohertz, which is more than what we are going to do with our measurements. And you can see now they're almost right on top of each other, right? So now that the resistor is way more dominant than the capacitor, and the capacitor is having hardly any effect on the circuit whatsoever. Okay? So anyway, so I just wanted to kind of show you the kind of things we're doing in the lab to make these measurements. But I'll provide you the measurements in a spreadsheet. Okay? Now I'm going to set up for the part 2, and I'll go through again just kind of a step-by-step demonstration, but I'll provide you the results with these ones as well, so you have the full set of results to do your report. Okay? Okay. Okay. So here we are for demonstration for lab number 2. And again, it's a lot better if you're going to be here actually doing the lab yourself. But what I'm trying to show you is, here's my connections to my power supply here. And what I have is the green is +5, black is ground, red is +12, and the blue is -12. And I also put the same colored leads here because that's going to help me keep in track of what I'm measuring. Okay, and then I've got my multimeter here. So right now, this is the red and the black lead from here. Okay, so right now it's across R1. Okay, now we can go through this pretty quickly. So again, what you're trying to do is fill out the table. So what we're doing is the R1 values. Okay, so right now I've got them. Well, what I'll do is we'll do it in the manner of the table, right? So right now what I'm going to do is I just take these two leads, the E2 and E3, and put them on the ground. And then now it only leaves E1. Okay, so this is R1, E1 is 6.95 volts. Okay. So R1 E2 is -0.92 volts. And R1 E3 is 1.14 volts. And now E all 7.17 volts. Okay? So now I'm going to move my meter to R2. So R2, E1, 4.92 volts. R2, E2, -4.02 volts. And then R2E3, -1.14 volts. And now R2E all is -0.25 volts. Okay, now I'm moving it to R3, E1, 3.22 volts. R3, E2, 0.61 volts. R3, E3, 1.13 volts. Now R3, E all, 4.96 volts. Okay, now I'm moving it to R4, E1, 1.7 volts. R4, E2, 0.32 volts. R4, E3, -2.27 volts. And then R4, E all, -0.25 volts. And then we move it to the last resistor, R5, R5, E1, 1.7 volts. R5, E2, 0.32 volts. R5, E3, 9.6 volts. And then R5, E all, 11.63 volts. Okay, so that fills out the whole table for the superposition theorem. Okay, but now what we want to do is we want to measure E Thevenin and R Thevenin. Okay, so what we need to do is we put the voltmeter across the R4, or in this case now it's the R load. We disconnect the bottom of this, so basically we're removing the R load resistance, and right now we are measuring the E Thevenin. So E Thevenin is negative 0.63 volts. Okay, and now to measure R Thevenin, I take all of these now and I put all of the sources on the ground, so all of the sources are removed. I change this to resistance, and there it is. That's R Thevenin is 705 ohms. Okay, so in our case now, okay, remember that we have resistor tolerances and things like that. When I build my circuit, okay, I'm going to use a variable power supply and I'm going to set it for 0.6 volts. Okay, and I'm going to say that the 680 ohm resistor is close enough to 705 ohms. And then we use, again, our 470 ohm for our R Thevenin. Okay, so let me just kind of remove all of this stuff. Shouldn't take me much time. Oh, here. Okay, and so what we should get now, when we measure, here in this thing here, we'll just get rid of this. Okay. Okay, I'll switch this back to voltage. Okay, and here we go. Everything's all tangled, but okay. Okay, so right now, so I've got my 0.6 volts, right, or 0.63, I think it was, right? And so it's supposed to be negative. I mean, if we get, again, all I need to do is switch the leads around and it would make a negative voltage, right? Use my negative as the positive, right? Let's just do that, just to make everybody happy, right? So now I'm putting negative 6 volts, and actually we can measure this voltage too here. Make sure it's right on. See, okay, so it's supposed to be negative 0.63. Negative 0.65 is pretty close. I mean, I can't dial it any closer than that probably. And then when I measure here across, and this resistor is just hanging here, right? So what I've got now is, so the voltage across the resistor is negative 0.27 volts. And in our superposition theorem, we measured it to be negative 0.26 volts. So again, it's like almost exactly right on. So even with our 680 ohm and not a 705 ohm and our 470, again, all of this stuff is turning out almost exactly the way we want it, even though we're just kind of making stuff happen here. Okay, so there we go. That's the end of lab 2. Again, so in a week, I'd like you to have the submission. Again, have fun with all those calculations. The measured stuff is way easier. So that just proves it. You got to want to come in and hang in the lab with me instead of sitting around calculating all this stuff out. You'll want to hang with me for sure. All right. So anyway, see you in 2 weeks for lab number 3. Okay. Thanks. Bye.